Welcome to the second video for the second problem of the second exam. In this video, we'll use the centroid we found in the previous video to determine the second moment of inertia, and then we will use that to solve for the strains at the top and bottom of the section and the stresses. Now that we've determined the centroid is at 1.38 inches up, and we have the n to transform our section, we need to find the second moment of inertia. That's pretty easily done, right? The second moment of inertia for a rectangle is equal to 1/12, the base, times the height cubed, and in general, you can use the parallel axis theorem and use its Ix plus AD squared. Yeah, I'll never get over how dumb that equation looks. Alright, so we've got that. This should be not too difficult now that we've got the transformed section, but we do need to have it transformed when we do this. So we're going to have, let's do brass first, and then we'll do tin. So that will be 1/12. The base is going to be 7.69 inches. The height is 1 inch. Cube that all you like, it's staying the same. Plus the area, which is going to be, well, 7.69 square inches. I hope you can figure out how I got to that one. Times, and then this one is going to be 1.5 inches minus 1.38 inches, whatever that is. Square that. Plus, now for the tin. 1/12, the base is going to be 1 inch, and the height is going to be 1 inch. Cubed, cool, very easy. Plus the area, again, this is going to be 1 square inch. Hopefully, again, you can figure that how I got to there. Should be pretty straightforward. In this case, it is going to be 0.5 inches minus 1.38 inches. I know that'll be negative. It doesn't matter. We're squaring it. So overall, doing all this, we're going to end up with 1.618 inches to the fourth. If you sort of have some rounding error, that's fine. So we'll use that in our equations for our stress. So our stress at the top, let's say, it's going to be equal to the moment, and by the way, the moment is 30 kip inches for this section. It's going to be the moment times the distance to the centroid divided by the second moment of inertia times n. Okay, and at the top, n is going to be pretty massive, because in this transformed section, we're imagining that this whole width is taking up stress when we use this. But it's not. Only 1 inch is taking up that stress. So in this case, it's going to be 30 kip inches times the distance, which is going to be, well, 2 inches minus 1.38 inches, whatever that is, times n, which is 7.69, no units there, divided by our second moment, which is 1.618 8 inches to the 4th, and we're getting 87.7 KSI. We can also check the bottom. We should also check the bottom. We should check the bottom. I'll use blue for that. But in this case, n will be 1 because we didn't transform this from tin into something else. I mean, if you want to, you can apply an n of 1 because the tin we transformed into tin, so n would be 6500 divided by 6500, which is 1. But for this one, 30 kip inches times, in this case it would be 1.38 inches times 1 divided by 1.618 inches to the 4th, and this is going to be only 25.67 KSI, which means that that this one, let's box it with not red, is our maximum at the top. Now for strain. So when we're doing the strain, we've got two stresses. Of course, we know about strain is going to be equal to stress divided by the Young's modulus. At the top, it's going to be 87.7 KSI divided by, at the top, we have brass, and that is apparently 50,000 KSI. Sure. And that's going to give us 0.00175 for our strain. I suppose you could argue it's negative because it's the top. And at the bottom, it's going to be 25.67 KSI divided by 6,500 KSI, and that's going to be 0.00395, which is the maximum. So the maximum stress is going to occur at the top, but the maximum strain is going to happen at the bottom because of the nature of the two different Young's moduli that we have to work with. That was a fun one. Now let's do 3.